All right, welcome to section 2.2. In these next few sections, really just about the remainder of chapter 2, our focus is going to be on quantitative variables, or the relationship between quantitative and categorical variables, which will account for much of the work that we do this term. All right, so initially we're going to look at measures of shape and center, and we'll look at also measures of spread. We'll look at measures of relationships with categorical variables, comparing distribution. So let's go ahead and get started. I'm going to take you through some material here. I'm going to try to highlight some of the R procedures, but I'm not going to dwell a lot because I want you to engage with the material and do some activities. And that will be the homework assignment for this week. Actually, for the end of the week, will have involved you applying this to some a data set. All right. Okay, so first of all, we start with the idea of a dot plot. So in a dot plot, each case of a quantitative variable is represented by a dot over the corresponding value. So dots are stacked to show repeated values, and it's especially useful for relatively small data sets with repeated cases that have the same value. So I'll give you an example of that. Now here's one constructed with R. Now this is not really a graph that R is very excited to produce for us, one might say, because the scale that's produced is, as I've noted here, kind of meaningless. It's just a count, but it doesn't even count the number of dots. So really you're focusing on the distribution of the dots here. We can adjust the size of the dots if we wanted to. Let me see if I can copy that into a window I've got open with R on my own computer. Pay no attention to what's already there. I think I don't need that. And let's see if it will let me do this. Okay, so I get this kind of plot. You can actually add an argument here and say dot size equals 0.5 and make them smaller or larger depending on the size of your data. So that's a possibility. All right. But it basically gives you the idea of the shape of the distribution, whether they're replications of values. And it's most useful really when you have a relatively small number of points with whole number values, so you can see where the data actually fall. In contrast, we can look at a histogram. Histogram is better for large data sets, and what we're plotting in a histogram is along the x-axis we have the scale of the data. So this is from the sleep study. It's data on the hours of sleep of students during the week. And the number of students is what's represented on the y-axis. So for each interval, it's telling us how many students in those particular intervals. So 7.5 to whatever this extends to. We could take a little time and try to figure that out. But for now, I just want to give you the sense that it's useful for thinking about what's the spread. It looks like there's some skewness here. That is, there's a tail coming off to the left with a few students who were underslept, perhaps exams, papers, or some other distractions late at night. Then here's the middle of the distribution somewhere here, and where it is specifically would depend on what type of middle we're talking about. And so at this point, it's useful to pause and think about what we mean by a histogram as opposed to a bar chart. Notice that in our histogram, there's no spaces between the bars. This has a quantitative scale to it. For a bar chart, we're summarizing categorical data, as we saw in the previous section. The x-axis has no numerical scale, and the number of bars is just the number of categories. Here, the number of bars is set by judgment, usually. And we might try a couple different interval settings, because the choice of intervals is going to give us a different picture of the distribution. All right, so some terminology here. When we say skewed left and skewed right, for skewed left, we mean the direction of the tail. So this would be skewed left because the tail goes off to the left. It may seem counterintuitive. You may feel that this is like starting with a symmetric distribution and shifting it over to the right. the way we would think of it is probably starting with something relatively symmetric and then it getting pulled out to the left or pulled out to the right. So we call that skewed left and skewed right. Other types of distributions we might look for when describing a set of data are symmetric or bell-shaped distribution, the famous normal curve. We may have an indication of symmetric but not bell-shaped or just clusters, right? Maybe there's a couple different groups, subgroups in the population that we can identify by looking at the X values and considering how the data were collected. Now, when we talk about an outlier, what we're talking about is a value that stands distinct from the rest of the data. If I go back to the sleep data that we were looking at here, maybe there's some extreme values, but maybe that's just typical of student sleep patterns and it's not really that unusual. But an outlier is an observation that's usually notably distinct from the others. Could be a data collection error. It could be a real observation that we want to pay attention to. In fact, it could end up being the thing that we're most interested in. In a pandemic, it could be representing a super spreader, somebody who's passed the disease on to quite a few other people. So we really would want to pay attention to that. Or in a survival analysis, one patient who survived a particularly long amount of time. So we would want to pay attention to this. Okay, now some measures of center that I assume will be pretty familiar, but I want to show you an applet that's kind of useful just to get a little bit of a sense of this. And you should find this on the lesson for this section, Moore's mean and median applet. So I think I have it open over here. So we can think of this as constructing a dot plot. It will let us just put some points on the scale here. So I'm going to put a few points and maybe one over here. All right, so this is perhaps an upside down plot or maybe a stalactite plot. So we can see that because it's skewed skewed to the right, there's a tail coming out or an extreme value. The mean is pulled out more. All right, it's the green value, the green arrow. The median is the red arrow at 2.04. Okay, and now if we move this point, see the mean is going to change, but the median is not. Now if we flip this over, we would see the property that's mentioned here that the mean is the balancing point of a dot plot or histogram. So if you put a fulcrum underneath this, and I had the point sitting on top, it would balance at this green point, and that's why when we pull a point out, it's moving the balancing point, but it's not moving the middle value. To move the middle value, we'd have to move something past the others, right, where it's actually changing what is the middle of the distribution. And notice the effect of an outlier on the mean. I'm going to trash this value and watch what happens with the mean. All right, it shifted over quite a bit. The median shifted slightly, but that's just because it's a very small data set. But the mean certainly changed markedly. Okay, and so that's going to be another property of the mean. It's going to be sensitive to extreme values. We can compute the mean in R using the function mean, if that's all we want. We can get the mean of weekday sleep. We can get the mean of weekday sleep according to whether or not the student had an early class. So for yes for early class, you get a little bit less sleep than those who didn't have an early class. And that would be the form that you would use, and you could copy that into R. All right, let's move on. Then the median of a quantitative variable. So this is where it's kind of much ado about very little when it gets into computing things. Often if we're working with real data or letting the computer do the calculation for us, but it is important to know what's happening behind the scenes. So we talk about the middle entry as being the median, all right, the middle of the data set. If it happens to be an odd number of data values, then the median is going to fall at one of the particular values. That is, it'll fall at the middle value. If the median is, if the number of observations is even, then it will be in between two values. So let's just see this. Maybe we'll take 6 values here. And here. So that was 6. So notice that the median falls in between these 2 points halfway. Now, if we change it to an odd-numbered value, then notice the median is now falling at a particular value, at the middle value. Okay, so that's an important property to be aware of, that if it's an odd number, then it will actually be occurring at the middle value. But what I'm most interested in is that you have a sense that the median is resistant to extreme values. It's not influenced by the tail and extremes as much. The medians are computed again by class and median weekday sleep. Resistance. I've mentioned resistance already. Resistance is this idea of a statistic is resistant if it is relatively unaffected by extreme values. And by extreme values we mean outliers, or by a long tail of the distribution. The median is resistant, but the mean is not, right? The mean is influenced by those extreme values. When a distribution is skewed, the mean is pulled in the direction of the skewness. So right skew means the mean is going to be more than the median. I should say indicates that the mean is greater than the median. Be careful how you use the mean here. Left skewness signifies or would correspond to the mean being less than the median, right? And finally, just to summarize this quick section, we're focusing on visualizing a single quantitative variable with a couple tools that I'd like you to get practice with. We look at the shape, and if we want to describe a distribution so far, we could talk about the shape and the center. And the important measure of center is, the important measures of the mean and the median. In many cases, we prefer the median because it's not going to be sensitive to an outlier. In other cases, grade point, right? We usually don't talk about the median grade point, but we would talk about the median income, because there certainly is a long tail usually in in income distributions. Okay, so that's probably a good stopping point. That kind of covers the essence of section 2.2. There'll be some practice problems to work on to kind of fix some of the ideas here, and I'll post those on Wiley+. Take care, and thanks for listening.